These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, what's the name of this device?
A concave mirror.
So I was just going for mirror, but yeah, it's a mirror. Which is the reflective side? Which is the front of the mirror?
The left.
Yeah, so I'm just using these dashes here to kind of indicate the back of the mirror. Okay, and you're right, it is a concave mirror because it's like you're looking into a cave. Do you know now, maybe I should back up a little bit. Maybe you should back up and write down what are the key equations for lenses and mirrors. So do you remember one of the key equations, or do you have in your notes one of the key equations for lenses and mirrors?
1 over... he writes it differently. Because I know it's like 1 over O. He writes like 1 over F equals 1 over S plus 1 over S prime.
Okay, that's fine. Those are fairly standard notations.
Okay.
He writes it differently from the textbook, you mean, or?
Well, and then I also learned like over the summer.
Right.
That's like 1 over F
I
plus 1 over O.
Yeah, that's right. So, all right, well, for this class, I guess we'll deal with it the way your instructor's writing.
Okay.
So I think this is the way it is in the textbook, too.
Okay.
Okay. So is this the formula?
Yeah.
Okay, good. Have you learned any other formulas? There's one other key formula for lenses and mirrors.
There's like the magnification.
Yeah, what's that formula?
M equals H prime over H.
There's another version of this formula.
And that equals negative S prime over S.
Okay, so these are the key formulas that we're going to be using for solving problems about lenses and mirrors. These work for both lenses and mirrors, so we're going to try to learn things that are always true for both lenses and mirrors so we don't have to go through everything twice.
Mm-hmm.
What does this symbol stand for?
The focal length.
Of the lens or mirror.
Of the lens.
Okay. So is this a property of the image or of the device?
Device.
That's right, it's a physical property of the device. This is the distance between what and what?
The focal point and the mirror.
That's right, this is the distance between the focal point and the lens or mirror. What does this stand for?
The distance between the object and the mirror.
Or lens, good. So it's called the object distance, but it's the distance between the lens or mirror and the object. And this stands for?
The image distance.
Good.
Distance between the mirror lens and the image formed.
Good. So is this a property of the device or a property of the image?
Image.
People often confuse these two, but this is a property of the device and this is a property of the image. You mentioned this is different notation that you learned before, but the notation actually makes kind of sense because this is where the object has been transformed into, so it kind of makes sense to call it S prime. What does this stand for?
The magnification.
Good. And this?
The height of the image.
Yeah, this is the height of the image. And this?
The height of the object.
And we already talked about these. Okay, so when you're solving problems about lenses and mirrors, you're generally going to need to plug into these equations. Sometimes you only need one of them, but most problems on the exam you'll need both of these equations. Sometimes you plug into this first and then you use this equation, but sometimes you plug into this first and then use this equation. Alright. By the way, notice this is really 3 different equations. What's one of the equations here?
M equals H prime over H.
What's another equation?
M equals negative S prime over S.
Good, and what's another equation?
H prime over H equals negative S prime over S.
It's good that you were careful with the signs there. So this is just a shorthand way of writing 3 different equations. So most problems on the exam, you're going to need this equation and one of these 3 equations, or maybe 2 of these 3 equations. Also, sometimes you start with the magnification equation and then you move to this equation. You don't always use them in the same order. Now, we've seen in physics one of the most important things is getting the signs right. So we want to make sure we know the sign conventions. So if I give you this concave mirror, what does that tell us mathematically?
The F is positive.
Yeah, that's right. So this is a hidden way of saying that F is positive.
Mm-hmm.
That's right. By the way, is this a converging or a diverging device?
Converging.
Yeah. And it's concave. So what does this tell you mathematically?
It's F is negative.
Yeah, F is negative. Is this converging or diverging?
Diverging.
Convex or concave?
Convex.
Excellent. What does this tell us mathematically?
That has a positive F.
Good, positive F. Is this converging or diverging?
Converging.
Convex or concave?
Convex.
Good. And what does this tell us mathematically?
Negative F, and it's diverging and concave.
Great. So, if something is diverging, what does that tell you mathematically?
It has a negative F.
And if it's converging?
Positive F.
Excellent. All right, so notice diverging lenses and mirrors both have negative F, and converging lenses and mirrors both have positive F. If you have a concave lens, what do you know about its F?
It's negative.
But if you have a concave mirror, what do you know about its F?
It's positive.
So what's kind of the more useful thing to think about? Converging, diverging, or concave, convex?
Converging and diverging.
Because it's the same for lenses and mirrors. So there isn't any rule for F for concave, convex that works for both lenses and mirrors. So the most useful thing to think about is whether it's converging or diverging. Okay, good. So this is a table that summarizes those ideas. So a common mistake people make is plugging in the wrong sign for F, because that's kind of a hidden type of information. Okay, so what do we know mathematically here?
The F is positive.
Because it's a converging device.
Mm-hmm.
Anything else?
The S prime is positive.
Yeah, change this. How about here? Is S prime still positive?
No.
So you're saying S prime is negative?
Wait, no, yeah, it is positive. But then H prime is negative.
Good, because it's pointing down below.
Mm-hmm.
That's right. Anything else?
S is positive.
That's right. Now, S is always positive.
Mm-hmm.
S is always positive except for some hard multiple device problems. But if there's only one lens or mirror, S is always positive. Good. Anything else?
H is positive.
That's right. Anything else? What about M?
Yeah, M is negative.
Because the image is inverted. Good. You could actually say even more than that, because is this image magnified or shrunk?
Shrunk.
I didn't, I drew it a little bit shrunk. What does that tell you about the M?
Small.
So what range would it be in? Wouldn't it be between -1 and 0?
Yeah.
It would be a negative fraction. So here we could actually say M is not just less than 0, it's between 0 and -1. Okay, so it's important to be able to take this information and translate it into math, so we can plug it into our problem here. Okay, very good. So this is an important exercise to be able to do. So now let's try it again with this example.
H is negative. H prime is positive. S is positive. S prime is positive. F is positive. And M is negative. And it's smaller, so M is between -1 and 0.
Okay, that's very good. So I wanted to point out the difference between M and H prime. So H prime here is positive because the image is pointing up from the principal axis, but M is still negative because this is the opposite orientation to this. Okay, good. Alright, let's try the same exercise here.
S is positive. S prime is negative.
Because it's a virtual image. Good.
Right. H is positive. H prime is positive.
Because they're both pointing up. Good.
F is positive.
Because it's a converging device. Good.
And M is positive. Yeah.
We can say a little bit more about M.
It's greater than 1.
So not only bigger than 0, but bigger than 1. Because this is a magnified image. Good. So one big mistake I see people make here is a lot of the time I see people say, oh, this is a virtual image, so F is negative. Because they confuse the image and the device. So it's not F that's negative here, it's the image distance that's negative. Or sometimes people say, oh, this is converging, so S prime must be positive. But S prime is a property of the image, not the device. Good. Let's try this.
Okay, so it's number one. So you have a concave mirror. An object is 30 centimeters in full length, so okay, so where do we start? Its F is positive 10. Its H is positive 5. And then for our formula, we can determine what S prime is. Oops. So that means that S is somewhere like here. And then we can determine the height. So H prime is -2.5. So then H prime looks something like, so then the image looks like that. But it should be smaller. It just doesn't look smaller. Oh. It's okay, I just redraw it. So it should be like that.
You need to change your pen.
Really?
Because, oh,
The pen
no.
looks really small.
Okay, huh.
That's weird. Okay. So that's image, and I can figure out the magnification. So the M is -0.5, which makes sense. Okay. And that's it.
That's good so far. Now on the test you might also be asked to draw the ray diagram, so let's do that too.
Oh, I don't know how to do that. The ray diagram. So, shoot, I don't know. I know you do something like this, right?
So far so good? Except there's no reason for that to be a dashed line, because
Okay.
that's real light.
Something like that.
Well, then let's work on that together.
Yeah.
Okay, So that's something else, that's a good thing for us to work on today, because it looks like you know how to do the math, but there's a good chance you'll be asked to draw the diagram too.
Yeah.
That's something you probably didn't worry about for the MCAT. Okay,
Yeah.
so let's talk about that. Let's see. You might end up needing a bigger picture. Also, now that we know ahead of time what our answer, oftentimes it's easier to draw the ray diagram if you know the answer ahead of time. For example, because I know I want the image to shrink, the diagram will come out better if I draw a big object, if you see what I'm saying. Okay. Alright, so this will be our picture. So we need two rays. So the first ray is called the P ray. Now you drew the incoming P ray correctly. It just goes like this. You know what P stands for? This means parallel to the principal axis. This is our incoming P ray. But it looks like you weren't sure how to draw the outgoing P ray. The outgoing P ray should go through the focal point. Hard to draw a straight line. So okay, so that's one ray. So you knew the incoming ray, but you need to know that the outgoing P ray is through the focal point. Okay. Now, what about the next ray is what's called the M ray. The incoming M ray goes to the middle of the mirror. M for middle. How do you draw the outgoing M ray? Well, that should be going out at the same angle it came in. By the way, is the outgoing M ray going to be on the left or the right?
Left.
Because this is a mirror, so that all the outgoing light is on the left. Sometimes I see people get confused about that. So here we draw the outgoing M ray. Okay. So where is the image? The image is where those outgoing rays converge. This didn't quite come out. What did you get should be your object distance? 15?
Yeah.
So actually that's not so bad. That's kind of close. All right, my picture didn't come out too badly. So here we would draw the image. Does this match our prediction?
Yeah.
From the math? How so?
Because we knew that S prime had to be negative. And that...
We knew that S prime had to be what?
I mean, we knew that H prime was negative, so
right.
it had to be
Good.
inverted. And we knew it was smaller.
And it did kind of come out smaller. Also, it came out real. And it came out inverted. Okay. Sometimes it can be hard to get the picture to get the... I have a hard time getting the picture to get the shrunken or magnified issue coming out right. But it should at least come out so it matches the inverted or upright. Okay. Okay, so generally you only need those two rays. There's other rays you could draw, but it'll probably be good enough just to draw the P and the M ray. Okay. So where does the outgoing P ray go?
Through the focal point.
Right, and how do you draw the M ray?
From the object to the middle.
And then?
And then leaving at the same angle.
Leaving at the same angle. Okay, good. Okay, so that's an important thing for us to talk about, but otherwise it looks like you got this problem correct. Anything else on this? Let's see. This would be 5 centimeters.
Yeah.
Okay, good. All right, but you did a good job working through the numbers. All right. something that I think can help you though. Is this picture here. This might be a good thing to put on your cheat sheet that you bring to the test. For example, if you have a converging device and you put the object here, what type of image are you going to get?
Real.
And what else does it tell us? Also inverted.
Oh.
And shrunk.
Yes.
How about if you have a converging device and you put the object here?
Real, inverted, magnified.
And if you put the object here?
Upright, virtual, magnified.
Those are the only three possibilities for a converging device. And there's only one possibility for a converging device. What type of image does the converging device give you?
Upright, virtual, shrunk.
So I'd recommend just copying this chart into your cheat sheet so you can check your answers, and also it can help to be able to predict ahead of time what your answer is going to be like. So how would we apply that to this problem? Which of the, so there's basically 4 cases. Which of the 4 cases would be in here?
F is 10. Logically surprised. It'd be inverted, real, shrunk.
Did that match our outcome?
Yes.
Okay. From now on, maybe we'll start with this. So when I give you a problem, you can first predict using the table, since you can bring that with you to the test, and then you can check it using your math. It also helps to draw the Ray diagram if you already know how it's supposed to come out in the first place. Okay, so since you can just bring notes, there's no reason not to use this table. By the way, this is an interesting special case. If you have a converging device and we put the object here, what happens to the image?
Inverted, real, same size.
So that's an interesting special case. Notice that's halfway between shrunk and magnified would be same size. So if we're right here, that would be a same size image. Right? Okay, neither magnified nor shrunk. Alright, now let's try this.
So the object is placed. I should probably drop bigger, huh?
Generally speaking, the bigger the picture, the easier it will be to work with, yeah.
project is 5 centimeters. So here's F. And so you know that F is positive 10 each. And then we can use the equation 1 over F. And then we can do H. H prime over H equals negative S prime over S. Oh, and then we should use this chart to predict. So it's at 1/2 F. So we predict that it'll be M be positive, S prime will be negative.
Focus on predicting it verbally.
Okay, it'll be upright, virtual, and magnified.
Is that matching your math?
So far it is.
Good.
And then we know that M is H prime over H, which is 10 over 5, so it's 2. So yeah, it should be magnified, and it should be at S prime of negative 10, so somewhere right here, and it should be like twice the size. Oops. And I guess now we can draw the ray diagram.
Right.
So it should just go straight across. And then to the focal point. Maybe, can I do it in a different color?
Well, are you allowed to use different colored pens on the test?
No.
Okay, so let's do it like the test.
Okay, so it looks like that, and then we do our second one to the center. Is it Command Z?
Yeah.
So then we just do like the virtual length. Yeah, and it works.
Good.
Yeah. Okay, I'm gonna fix it. That's probably. But yeah, this is like where it intersects, and that's where our picture is.
Okay, now does this match our predictions from the table?
Yeah.
Upright, yes. Virtual, yes. Magnified, yes. Okay, well good. This usually gives people trouble, but you worked this out. So what you saw here is, if you have a real image, the image is where the outgoing light rays converge. But for a virtual image, that's not the way it works. As you figured out, for a virtual image, the image is where what I call their tracebacks converge. So you noticed here, the outgoing light rays here would never converge, at least if we drew them with accurate angles. You had to trace them back to get them to converge. And this is where it helps to have known ahead of time that you were expecting a virtual image. It can be easier to draw the picture, because it's hard to judge the angles otherwise. Okay, so that's an important point. So for a real image, like the previous example, the image is where the outgoing light rays converge. But as you worked out here, for a virtual image, the outgoing light rays will never converge. That's why it's virtual. Instead, the image is where their tracebacks converge. And that's when you shift to the dashed lines, because there isn't actually any light there. So that was a good decision also to shift to the dashed lines. Okay, good. So you adjusted to the virtual image correctly there. So that was a good process for solving that problem. Good. All right, well, when you're ready, let's try problem 3. I guess I should say this. All right, so here's problem 3.
So now it's a convex mirror. And an object is 5 centimeters from it. With the focal length of -10. The object is 5 centimeters high in its place. Okay. So from our prediction, it's convex, so it's diverging. So we expect it to be upright, virtual, and shrunk.
Excellent. So it's easy to predict for a diverging device.
And we know that F is -10, S is 5, and H is 5. So we can just like do the math. Or I guess, okay, I'll trace first. So this should be and then so I expect it to be here. But it should be shrunk, so maybe I'll fix this. It should be like smaller, right?
So now that, since you know it's going to be smaller, it would be easier to draw the picture if you had drawn a bigger object.
Yeah.
You could have gone back and checked that right now, as long as you're erasing everything else. That's the advantage of knowing the prediction ahead of time. If you know the prediction ahead of time, since you know you want it to shrink, your picture will be easier if you draw a large object.
Okay.
On the other hand, if you knew you wanted it to magnify, your picture would be easier if you drew a small object.
Okay. This should go like that. And then
You should check with your instructor. Some instructors will let you bring a straight edge to the test. So if they let you do that, that'll help you on the test.
okay. Thanks, that's where our object should be. And then
Image.
The image, yeah. 1 over negative 10 equals.
Does that match your prediction?
Yeah.
Good. Let's talk about the ray diagram here for a second. So, are we dealing with a lens or a mirror?
Mirror.
Which side is the incoming light on? Which side?
Side.
On the left. Good. So why don't you put arrows showing the incoming light direction? So which side should the outgoing light be on?
The right.
For a mirror?
Oh, to the left.
Because a mirror reflects, right?
So
A mirror reflects. So the outgoing light rays should have been on the left-hand side. Now, you didn't really make a mistake. The point is, the image is not going to be where the outgoing light rays are, it's going to be where their tracebacks are. But these should be dashed, right? Because these are tracebacks, they're not the actual outgoing light rays. There isn't, because of course this would just be a wall, right? There wouldn't actually be any light on the right side of the mirror. That's a good job of making it dash.
Okay,
Good. So let's also draw the actual outgoing light rays. How would you know how to draw this light ray?
Same angle as this.
Yeah, it should be the same angle as the incoming light ray.
And this should also be the same angle. Oops.
Yeah, how do you know how to draw that outgoing light ray?
Should be like, and that should be the same angle.
Same angle as what?
As this one.
No. After all, this light ray is horizontal. This is not horizontal, so they can't be at the same angle. So remember, what was the name of this ray?
The M.
Yeah, maybe you should put an M there to label that as the M ray. That goes into the middle and out at the same angle, but this is called, So the incoming P ray is parallel to the principal axis. How do you know how to draw the outgoing P ray? In a way, you've already done it. So yeah, do you remember how do we draw the outgoing P ray?
It should hit the focal point.
It should be going through the focal point. That's right. But actually, it's more complicated than that. The outgoing P ray, or its traceback, should be through the focal point. In this case, it had to be the traceback that was through the focal point. So that tells us what this angle should be. This should just be in line with the traceback, which is through the focal point.
So this angle right here should equal this angle right here.
I suppose that's true, yes. Those will be equal to each other, that's right. Or all you have to do, that's correct. Although you could just say it more simply, draw the traceback through the focal point and then extend it as a straight line. You're just extending this dashed line as a straight line, and then that'll automatically. So instead of thinking what should the angle be, just extend your traceback as a straight line. Okay. So even though your original picture found the right place for the image, we wouldn't get full credit for that because we're not actually showing the light. The light is actually bouncing off in this direction. So what happens is that as you get more virtual images, sometimes you have to work more with tracebacks. So what did we learn about the P ray? How do you draw the outgoing P ray?
It has to be parallel with the one that goes through the focal point.
In line with the focal point.
Yeah,
So all I'm saying is the outgoing P ray either goes through the focal point or its traceback goes through the focal point. In the previous cases, the ray itself was going through the focal point, but now it was the traceback. One thing that you did well here is that you realized that the focal point shifted to the right-hand side. The focal point is on the concave side, so to speak. So this is the correct focal point. Okay, so this would be a good one to mark and practice again, because that gave us, the ray diagram gave us a little trouble. That's a good way to be careful with the signs.
Is each prime, so 10 over 3 over 5. So 2 over 3. which makes sense with what we predicted.
It does seem to have shrunk to 2/3 of the original size. It might also help to change this into a mixed number so we can compare, which you can see is less than 5.
Right, yeah.
Okay. Okay, and if you were going to give answers, you'd put units on all of those. Okay, good. Okay, so you're not having any trouble with the math. Sometimes there's some tricky parts here with the ray diagram. So actually, I think the previous ray diagram you did fine on. So the key thing here is, remember, the outgoing light from a mirror is always on the same side as the incoming light. However, you might also need to draw the tracebacks for the outgoing light, and that's what we use the dashed lines for here. Okay? And we also saw some tricks. If you know ahead of time that your image is going to be shrunk, you may as well draw the object big.
Right.
Okay, let's try this problem.
So for an object. So now it's a convex lens. So it looks like this. Right?
That's good enough, yeah,
Is
good.
that
You might want to fire your optometrist there, but yeah, it's hard to draw, so that's good.
okay?
The left side looks good.
Whatever.
Somewhere
Okay, and now
to the right side.
is 30 centimeters from a convex lens. So this should be like our object with a focal length of 10. So that means it's farther away from F. It's convex lens, so it's converging. And it's farther away, so we know it's going to be inverted, real and shrunk. So I should draw like really big. Yeah. And so it's, okay, so it's 30 centimeters from it. It's going to be inverted, real and shrunk, so we know it's going to be somewhere here. And we know our F is like here. And this is, okay, well, this is supposed to be 5 centimeters and this is supposed to be 30, but it's clearly not to scale, but I guess it's okay.
You mean your vertical axis is not in scale with your horizontal?
Yeah.
That's fine. Yep, that's okay.
So I guess I'll just draw this now. Shoot. Okay. Make you taller. Okay. And then we know it's got to go through the focal point.
Okay, now this is our first lens problem. So one tip for lenses is you draw the change at the midpoint. So what you should do is,
Oh, I should put like a dotted line in the middle or something.
and you draw the changes happening here. All this stuff over here is just cosmetic. We're not actually using the picture of the lens. We're just changing the angle at the midpoint.
Okay. So okay, let's see. Well, okay, let's just erase this. So it should go to here. And then And then this has
Now, what's the name of the ray you just drew?
the P.
Good. Let me give you a little help with that. Are we dealing with a lens or a mirror?
It's a lens.
So which side is the incoming light on?
The left.
So which side should the outgoing light be
The
on?
right.
Yeah. So I think you were still thinking in terms of a mirror here, because we just did a bunch of
Yeah,
mirror
I
problems,
wasn't
but we need to
sure.
shift gears.
Okay.
Okay, let me help you a little with that too. So one key thing is that we saw that when we did it with mirrors, a mirror has only one focal point, right? Lenses have two focal points because they're symmetric. There's a focal point here and a focal point at the same distance on the right-hand side.
Okay.
And you need to figure out, should we draw the light ray through this focal point or this one? Well, remember, is this a converging or a diverging device?
Converging.
So do we expect it to bend the light up or down?
Down.
Down. All right, so I think we made the wrong guess the first time.
Okay, so I have to erase this whole thing.
Yeah.
Okay. Okay, and then this thing goes to the midpoint.
By the way, what are we expecting for our image, real or virtual?
Real.
So are we going to be using the outgoing light rays or the tracebacks?
Outgoing.
So there's not really much point drawing that traceback there. Of course, it won't mess you up, but since we know we're going for real anyway, we know the tracebacks won't be too important to us.
Okay.
Yeah. Sometimes the tracebacks can still be helpful for real, for getting the right angle, but anyway.
Sorry, this keeps messing up.
That's okay, that's fine.
Okay. And then it should go up at the same angle. Relatively. So that's where our image should be.
Good. Now check, would that match the inverted?
No.
So we must have made a mistake. Now remember, is this a lens or a mirror?
It's a lens.
So just use your common sense for a lens. How is this light going to move as it goes through the lens? It's not going to bounce up like this. You kind of treated this principal axis as a mirror here. There's actually no reason for it to bounce up like that.
Okay.
How would the light actually move through that lens?
Oh wow, assuming it goes down. Okay, so we have that. Down.
Yep. At what angle?
This angle.
The same angle it came in. So you don't even have to think about the angle. This is just a straight line. The M ray is actually very simple for a lens. It's just a straight line through the middle.
Okay.
Yeah, it's hard to draw. But if we drew it correctly, it would be a straight line through the
Anyways.
middle. That's fine.
There should be some point here where they intersect.
Right.
And it should be shrunk, but it doesn't.
Yeah, but that's hard. I have a hard time getting that to come out right too.
Okay.
I have a hard time getting that to come out right too.
We'll just pretend like it shrunk this
Yeah.
way.
The key thing though is to make sure that it comes out inverted and real.
Okay.
All right, but again, you might ask your instructor whether you can bring a little ruler so that you can make your diagram to scale, and then it'll be more likely to come out right. One reason this didn't come out right is because the object here, let's see, in the information, the object is 3 times the distance of the focal length, right? But you kind of drew it just twice the distance of the focal length. And actually, remember, if you're twice the distance of the focal length, the table predicts that you'll get the same size image. So actually, given the way you drew it, it came out pretty good. It came out the same size. So if you were going to draw this picture again, the best thing to do would be, all you have to do is put these focal lengths closer to the lens. If you had put the focal lengths closer to the lens, then the picture would have come out better. All right. And how would you know to do that? Well, if you know your prediction ahead of time, that can help. All right. So let's...
And then how did you know it goes through this one instead of this one?
Because which way do you expect a converging device to bend light? Do you expect it to bend the light up or down?
Down.
Yeah, because otherwise these wouldn't converge, would
Oh,
they?
so then this one also goes down. So that both of them will go down.
Yeah, so this is moving towards the other one.
Okay.
This one's moving towards the other
But
one.
then this one's moving away.
Hmm?
The bottom one's moving away from that one.
But the point is, yeah, so the point of a converging device, the converging device doesn't necessarily make the light rays move towards each other. It moves them closer to moving towards each other. Notice here, there's a big angle. Incoming, there's a big angle between the P and the M, and now there's a smaller angle between the P and the M. So all the converging has to do is make them closer to converging with each other. In this case, it actually did make them converge with each other. All right, so let's review those a little bit. So for a lens, the incoming P ray still goes to the focal point, but now you have to remember there's two focal points, and you have to decide which one to use based on the fact that it's converging. So here's how you figure it out. If you have a converging lens, the outgoing ray goes through the focal point. Oh, looks like this version is outdated. Let's see here, diverging. Okay, yeah. If you have maybe this will work. So for a converging device, the outgoing ray goes to the focal point. For a diverging device, the traceback of the outgoing ray goes through the focal point. So I think that'll work for both lenses and mirrors. So since this was a converging device, we expected it was the actual outgoing light ray that went through the focal point. All right, and how do you draw the M ray for a lens?
It's just a straight line through the midpoint.
Yeah, it's just a straight line through the middle. Remember at first you thought that it was going to bend upwards, but that doesn't actually make sense physically. For a lens, would just let the light go through. Okay, so that's another good one to go back and try again. And you know, I think you already know how to use the equation, so let's just focus on the diagrams now. So I'm sure you could get the right answer with the numbers. The thing for us to work on is the ray diagrams. Okay. Alright, let's try this one. I guess this is, I lost track. Number 5?
Yeah. So it's a convex lens again. So it's going to look like this. And then an object is 15 centimeters from the convex lens. And the focal length is 10. So you would expect it to be inverted, real and magnified. So we can draw like it's kind of small. And then our F should be like here, and it would also be here. So then
it's a converging device, so the outgoing ray went through the focal point. Good.
oh no. Okay.
Yeah, I have a really hard time getting them to come out right too.
Wow.
Basically what you can do is cheat. you know you want it to come out, actually it didn't come out so bad, they just didn't converge.
Yeah.
Actually, it didn't come out so bad. You just have, sometimes you kind of have to cheat the lines to make them match.
Okay.
All right, at least it's coming out magnified,
Yeah.
which is what we wanted.
Okay, that's basically it.
Okay.
So this is where our object should be, which makes sense because we want it to be inverted and magnified and real.
Did it come out real?
Yeah.
Okay, good. Okay, so again, we'll skip the math because I think you know how to do that, but that's the way to draw the picture. Okay, good. Let's try number 6. Unfortunately, there's lots of different cases.
Okay, so it's 5 centimeters from... So it's a convex lens. Five centimeters from it, or hoping for 10. So this is F. This is where object is. So it's less than F, so we know it's going to be upright, virtual, and magnified. So I should probably just draw it like small.
That's a good idea.
And then, so do this, and it's going to do that, and then it's virtual, so it'll do the trace back.
That's good. So because this is still a converging lens, the outgoing P ray, it's still the outgoing P ray and not the trace back that goes to the focal point. Good.
And this will just go straight, and the trace back. Somewhere right here. But then that's on the F. I don't know if that's right.
Yeah, it probably wouldn't be exactly on the F, but let's not worry about that.
Okay.
As long as we get the right qualitative properties.
Okay, sorry, it was bugging me. Okay, we'll put it here.
Okay.
So then, yeah, that gives everything, because then we know it's upright, it's virtual, and it's magnified.
Okay, that's very good. So you adjusted well here. So one thing you saw is, for the P ray, it's still the outgoing P ray that goes to the focal point, but we do need its trace back too to find where the image is. So we need the trace back for the image, but we're still using the outgoing P ray to go to the focal point. Good. You might want to put some arrows on your light rays to show what their directions are. But that's a good picture. All right, so now let's try number 7. Let me call this, let's call this 10 centimeters.
So it's a concave lens. So it's going to look like, so it's 3%. Like that-ish.
That-ish, that sounds good.
And then it's 10 centimeters from the concave lens. So like somewhere here with the focal length of 10 centimeters or negative 10.
Negative
I
10.
guess it doesn't really matter. So here's F, And this is also F, but the image is on F.
The object.
The object. So we know that that means that, and this is concave, so it's diverging. And diverging, then it's upright, virtual, shrunk. Okay. Oh, then I should draw this bigger.
Okay, good. Yeah, so having a good eraser is important for these problems. The picture comes out better if we're willing to change our picture.
Yeah. Ugh, then I should draw this thing bigger. Ugh. Okay.
Good.
Okay. So this is gonna go like that. And it's diverging, so it's gonna go up. And we know it's gonna be a virtual image, so it has to do with whatever the trace back is doing. But the trace back has to go through the focal point, so I drew that. And then
Okay, so let's talk about that for a second. That's good that you thought about that. So how do we know what angle this line is going at, the outgoing light?
because this trace back has to go through the
Yeah, so it should be in line with the trace back. So if we were really trying to draw this to scale, you'd have to draw the trace back first.
yeah.
Because what you did here is you just picked an angle at random for this
Yeah.
light ray to go at. So if you were trying to get it to scale, first you would draw the trace back and then you would extend outgoing light like that. Okay, so that's good. So this is the first example of what we saw here from the handout. For a diverging device, for the outgoing P ray, it's the trace back of the outgoing ray that goes to the focal point. So we've seen that's a little bit trickier for lenses than for mirrors because lenses have two focal points. So now we've seen all the different cases of how you decide which focal point to use. Okay, so you figured that out correctly, good. And you can see this really is making the light diverge.
And then the N has to go through the midpoint. And then it's diverging. So it's gonna go, it's just gonna keep going down. Is that right?
What do you think?
Well, it's diverging, so would it jump up?
So how did we say that we're supposed to draw the M ray for a lens?
Oh, just straight through that midpoint.
Right. And you can see that the outgoing light rays now really are diverging from each other.
And I guess, does it also have a trace back doing this?
Yeah, so you don't really even have to draw the trace back because the trace back is in the same position as the incoming light. You can't really see the trace back because it's in the same position as the incoming
So
light.
then this would be our object, which makes sense because it was supposed to shrink and be upright and be virtual.
Okay, good. So the thing that gave you some trouble here was the M ray. So this is another useful part of the handout that you might copy onto your cheat sheet. So notice for the M ray, for a lens, the M ray just goes out along, the M ray is just, goes into the middle and it's out from the middle along the same line. So does the M ray bend for a lens?
No.
No, the M ray does not bend for a lens. Does the M ray bend for a mirror?
Yes.
Yeah. Here's an M ray that's bending for the mirror. But notice we never had any pictures where the outgoing light was being bent upwards by the principal axis. Yeah, I think you're kind of thinking of the axis as if it was like a mirror itself, but it's just an imaginary line in space. So we never had any M rays that were bending like this. The trace back is bending up here, but not the actual light. Okay, so it would be a good idea, so we went through about 6 or 7 of the possible cases, so it would be a good idea to just practice all of those again on your own so that you're comfortable with those when you see them on the test. It's time consuming because there's a bunch of different cases, but those are the things that you might see. Alright, good. Let's see. Okay, let's try this.
So it's a convex lens. So it looks like that. Object is 10 centimeters from the convex lens. So, you know S is 10 centimeters. You know M is 2. So if M is 2, yeah, and then an object 10 centimeters has a virtual image, okay. It's a virtual image, so you know the image is going to be formed somewhere here. It's okay, so, well, I don't know what the focal point is, but I guess I can just draw this. Oh, I don't know what the focal point is, so I feel like that won't do really good. I know that S prime is going to be positive. And since I know that the image is virtual.
Okay, let's work on this together a little bit. So, so now we're moving on to the harder types of problems that you might see on the test. So, first of all, could you use our table to predict anything about the answer? What region are we in our table?
This region.
Upright, virtual, and magnified? Okay, because it's a convex lens, and there's only one region that would give a virtual image for a convex lens, and that confirms it's going to be magnified. Okay, good. And then that tells us the image will also be upright.
Right.
Okay. Why did you say S prime would be positive?
Because it's going to be virtual, so you know it's going to be tracebacks, and it's a converging lens.
So let's review
Actually, just kidding. It's going to be this way.
Yeah, let's review the sign convention for S prime. When is S prime positive and when is it negative?
I don't know. S prime is positive. Well, S prime is positive when it's this on this side of the lens.
When the image is on the left?
When the image is on the left.
Okay, actually that's not the best way of thinking about it. Maybe we should have done some other examples of that. So it's actually a simpler rule than that. S prime is positive for real images, and S prime is negative for virtual images. S prime is positive for real images and negative for virtual. So it sounds like we were overcomplicating that. So, So by the way, when S prime is positive, if we have this lens, here's the object. If S prime is positive, which side will the image be on? Left or the right?
Right.
Actually the right, which I think is the opposite of what you were guessing a second ago. By the way, if this was a mirror and S prime was positive, which side would the image be on?
Left.
Good. So that's why it's actually not a good idea when you're learning the sign convention here to focus on left or right, because we want to learn rules that work for both lenses and mirrors. Thinking about it in terms of whether the image is on the left or the right, or the same side as the object, that's confusing because that gives us different outcomes for lenses and mirrors. It's better just to say real image always gives us a positive S prime, and virtual image always gives us a negative S prime. Okay, so let's see, moving back here. So what do we know about S prime?
It's negative.
Good. Now you said your M was 2?
Yeah.
Positive or negative 2?
Positive.
How do you know?
Because it's upright.
Here's where the table helps us. Yeah. So we know it's going to be upright, so that's going to give us an M of positive 2. Okay. And is H prime going to equal 2H or negative 2H?
2H.
Because it's upright, again. Okay, write down your magnification equation. Excellent. Now let's try plugging in.
Oh, okay.
Now remember that equation is really 3 equations in one. Which of the 3 equations is going to be helpful to us here?
This one.
Okay, and that confirms our prediction there.
Yeah.
So notice the key thing here is most people get stuck here because they expect to use the reciprocal formula first. But this is a case where it was more useful to use the magnification equation first. But now let's use the reciprocal formula.
So F equals 20.
Does that make sense? Does F equal positive 20 or negative 20?
It's positive.
That came out positive from the math. Is that what we expected?
Yeah.
Because it was a convex lens. So that's another way to check our work. That's something we could have predicted ahead of time, actually, that F would come out positive. Okay, well now I think we've ended up figuring out just about all the variables, right? We figured out F, we figured out, and S prime, right? We figured out F and S prime, which are the 2 things they'd be likely to ask us about. Okay, so how were we getting stuck on this problem? One thing that was getting us stuck was this sign convention for S prime. So it's a simpler rule than I think you might have realized. It's just real means positive S prime, virtual means negative. Also, I don't know whether you thought about this or not when you did this. Notice you can't just say M equals 2. You have to decide, is it positive 2 or negative 2? We got a little lucky here because it turned out to be positive, but you got to make sure what, so notice when they say it's 2 times the actual size, that could mean M equals positive or negative 2. So that's something to watch out for on this problem. And then once you've written this down, you just plug into these 2 equations. Notice that in this case, it actually helped to work with the magnification equation first, and then go to the reciprocal formula. All right, now we should be able to draw the array diagram.
F is 20. We know that this is 10. So F is like out here. It's also like right here. And we know that it's virtual, so it's going to be the trace max. like something right here. Which makes sense, because we expected it to be upright, virtual, and magnified.
Good. Okay, good. Why don't you label this with an S and this with an S prime, so you know who's the object and who's your image. And also, it's a good habit to get into to draw those arrows. Okay, good. Okay, all right, so now we started to see how they can make these problems more complicated on the math side. So this would be a good problem to go back and try again. One more thing though, maybe on that problem. How did we know that m was going to be positive?
From this.
Yeah, but I'm not sure whether they'd let you use that on the test as your explanation, if you know what I'm saying. I'm not sure you can say, oh, I know this is positive because I have this cheat sheet on my chart. So let's see, how do we know that m is positive here? Where was the problem? It was a virtual image. All right, so here's the key thing. Notice, are virtual images inverted or upright?
They are upright.
Yeah. Check our chart. Is that?
Yeah.
And how about real images?
Inverted.
All right. I think they would. I don't think you have to prove that. You could just say we know that virtual images are always upright and real images are always inverted. So if this is virtual, that means it's upright. So does that tell you that m is positive or negative? All right, so I think you would probably want to give that little explanation. You can't just say I have a chart that says this is the answer, but you can say we know that virtual images are always upright. That's a fair thing to have memorized. And then you can say upright means positive m. That's how you would know. Yeah, that's how you would explain it. So the chart is just there like as a backup. Okay. So you can see one of the keys to these is thinking about the signs. Oh, I'm sorry. Let's change this. All right, let's change this to this.
You have a concave mirror. So we know it's a concave mirror. So it's convergent. So F is positive. So F is somewhere here. And we know the radius is 20. So let's say this is R. And then F is 2 times R, right? And that's the equation. Let's see. Oh, okay, I'll forget about that. Or, okay, I'm not. Is F equals 2 times R? Let's see. For mirrors, yeah. Or F is 1/2 of R. Okay, so that means F is right here. So F is going to be 10 centimeters. R is 20. The image is above the head, is above its length. The image is above, we use a concave mirror. We have a real image of a doll. Well, since it's a real image, and it's the same size, and it's upright. It's upright and the same size, and it's real. But none of these give me that. But then is it inverted?
Now, those are two different mean. Why did you say it's upright?
Because the doll's head is above its legs.
Yeah. Now, That's not the way we've been using the term upright, though. We've been using upright to mean oriented the same way as the object.
Yeah.
But those are two different things,
Oh,
because we don't know whether the actual object has the head above the legs or not.
That's why I just assumed that.
Yeah, so that's something we can't assume on this problem. So in the ordinary English sense of the word, this image is upright, but not in the optic sense. In the optic sense, we can't tell whether it's upright yet, because we'd have to compare it to the object. So that the word upright is a little bit unfortunate here. When we say upright, we mean oriented the same way as the object. So the way this problem is written, we can't assume that the actual doll has the head above the legs. That's something we have to figure out.
Then I feel like there's nothing else we can get from this.
Are you saying there's nothing more we can figure out?
Yeah.
Now, did you find where we were in the chart?
But I don't know if it's inverted or not.
Ah, well, the point is, there's only one place in the chart we could possibly be. There's only one place in the chart that gives you a same size image. Notice, nowhere else in the chart would give you a same size image.
Okay.
There isn't any place else. Technically, if it was right on top of the lens, it would be same size, but that's impossible. So there isn't any place else in the chart that would give us the same size image. So we know we must be there.
The doll then is here and its head is upside down, right?
Good. Because the chart said it's going to be inverted.
Or would this be drawn, or am I, no. So then S is 20. H, we don't know what H is.
How did you know S was 20? From finding ourselves on the chart. Good.
And then 1 over F equals 1 over S plus 1 over S prime. 1 over 10 equals 1 over 20 plus 1 over S prime. So S prime equals 10. That means our image is here. Which...
Whoops, slow down. Let me think about this for a second. When did you get S of 20?
Because it says we have a real image. Oh, from this. Because our, you know that our object is 2F. Is at 2F, and 2F is 20.
That's true. Alright, 1 second. We're making a mistake somehow. So. How did you get this? S prime equals 10.
This would be 220 minus 120. Oh, it's 20.
Okay.
Okay, so S prime is 20. The S prime is here.
Good.
Okay. And we know it's real. Okay, let's just assume it intersects here.
Okay.
Then it intersects here. And an image doll's head is above its legs. So this is probably this is the legs and the head is here. I think. So they intersect somewhere here. And this is the head, and these are the legs.
So have we satisfied the conditions?
Yeah.
You check all of them?
Yep.
Did you see the part where it says the image is above the central axis?
Yeah, so this is wrong.
Okay. You're close.
Okay. Well, okay, but it's real. So like that doesn't make sense to me because then it wouldn't be the virtual or wouldn't be the trace backs.
Okay, so first of all we should try drawing the image because that's what we know the most about. So should the image be standing on its head or on its feet?
What's feet?
And should it be above or below the axis?
Above.
That's what you should have drawn first because that's what we know. So the mistake you made was you drew the object first. But what we should draw is the image first, because that's what we know. These problems are harder than the ones I gave you before because we have to work backwards. For easy problems, we draw the object first, but here we don't know enough about the object. So we should have drawn the image first like this. Of course, the object and the image would also be in the same place horizontally, but I'm not going to draw them that way. So far, so good. Now, draw the object.
Should be the exact same side.
Good.
And inverted, so the head's below its feet.
Good. And should it be above or below the axis?
Below.
That's how we were getting messed up. So try drawing the object now.
So it should go like that.
Okay, so you were close before.
Oh, man. So should I erase this whole thing?
You need to, well, kind of, you just have to flip who you're calling the object and who you're calling the
I'll
image.
just redo this whole
Yeah.
thing. Wow.
Yeah, why don't you do it, actually, yeah, why don't you do it from scratch, because the ray diagram isn't quite right.
Let's just start from the beginning. So this is our and then we know this is F, and we know that S is here, which is R, and we know that, so this is our image, so then our doll has to be like this. This would be the same side. And so this goes like this.
It's hard to make it come out right.
Anyway, somewhere here.
Okay. Okay, so now we're doing some harder problems than we did before. So all the earlier problems, I always gave you objects that were above the principal axis. So you just kind of assume that they're always that way. But there's nothing that says that in real life you have to do it that way. So this problem faked us out by having an object that happened to start below the principal axis. Okay, so this is a case where we kind of have to work backwards.
Does it matter, like, so I mean I started drawing it from the head. Does it matter if you're drawing from the head or like?
You generally should use the furthest point on the object, so maybe it would have been better to start with the tip of your head.
Okay.
Okay. But it's not a big deal. The only point is, what you're doing now is you're trying to, this point should be, you actually drew it, say, from the guy's nose. So this should be where the nose of the image is.
Okay.
Okay. One thing that we saw here is the word upright can be kind of misleading. Is this image upright or inverted?
Inverted.
Yeah, it looks upright in the normal English sense of the word, but it's inverted in the optics sense because it's oriented differently from the starting material. So notice, just because the image has its head above its feet doesn't mean that it's upright in the optics sense of the word. All right, so that was something we had to work on. So let's go back and review the steps here. One thing that you did well here is you saw that radius is not the same thing as focal length. So we haven't talked about that, but you must have seen that before. So that's one of the formulas that you'll need to have on your cheat sheet. At first you were misremembering the formula. I think you thought that F was 2R, but it's actually R is 2F. So what was F on this problem?
10.
10 or negative 10?
10.
How do you know positive 10?
Because it's to the left. What's in here?
No, that's a confusion. How do we know that F is positive 10?
Because it's a mirror? I don't know.
Take your time.
How do we know it's positive F? Because it's,
Let's see. Well, I guess you actually, did you figure out F in this problem, or did I tell it to you? Oh yeah, well I gave you the radius was 20 centimeters, and then you said F was half as big. But how did you know it should come out as positive? So I think you might have forgotten what the sign convention is for F.
Because it's converging, right? I wrote that here.
Yeah, because it's a converging mirror. Therefore, F is going to be positive. How did we know it was going to be a converging mirror? Oh, because it's a concave mirror.
Yeah.
Okay. So, by the way, R here is positive 20. So notice this equation doesn't tell you, R equals 2F doesn't give you the signs. It only gives you the magnitudes. That's why I put in the dots here. All right, that's something to be careful with. Then you got that S was 20, right? How did you know that S was 20?
This.
Right. By the way, now, at first you didn't want to use this because it said inverted, but now we can see the image really is inverted. But the problem is, this might not be a good enough justification on the test. You can't say, oh, I know S is 20 because I have that written down on my handout, that this is the case. So how can we prove that S is 20?
How can we prove it?
Or give a reason for it? I guess we really do want to kind of prove it.
I'm not sure.
So one thing you should be thinking of is that we've only used one of our equations so far.
Right.
On a hard problem like this, we almost always need both equations.
So, this equation?
That's right. Now we know that's really 3 equations in one. We want to choose the one which is most helpful to us.
Oh, this one. So 1 equals negative S prime over S. Because they're the same height. So
Now, that one, this is actually hard. Let me help you with this. That actually turns out not to work because you don't know yet whether, so you're saying that H prime over H is 1. But you actually don't know yet whether it's 1 or negative 1, right? Because you don't know what the relative relationship is. So that actually turns out not to be the most useful equation. Here's the trick you need to use. We should have already figured out here what M is. What is M?
1.
1 or negative 1?
Negative 1.
How do you know?
Because it's inverted.
How do you know it's inverted?
Because,
We need an answer that they would accept on the test. We can't just say from the table.
chart says it. And
Now this is a real image,
oh, right.
and real images are always,
Inverted.
I think they would accept that on the test. You could just say, we know that real images are always inverted. real, we know that it's inverted, because real images are always inverted. And since it's inverted, what do we figure out from that?
M is negative.
That m is negative 1. Okay, so I think you need a little explanation like this probably on the test in order to explain how you know that m is negative 1. All right, and now what? I don't know, now what?
Wait, what are we doing?
We were trying to show how we knew that s was going to be 20.
Oh, then we know that m is negative. So then... Okay, we know m is negative 1, so negative 1 equals negative s prime.
This is actually hard. Okay, yeah.
S prime equals s.
Okay, that's actually as far as you can go. We don't know that s is 20 yet. Actually, the table here was a huge shortcut. Without the table, this is much harder. All we know is that s prime is s. All we know is that s prime is going to be equal to s so far. Okay, so now plug into the other equation.
This one?
Yeah, the reciprocal formula. No, the reciprocal formula. So let's write down 1 over f equals 1 over s plus 1 over s prime. Now, when you did this before, you plugged in 20 for s. But remember, we really can't do that on the test because we haven't proven that yet.
If these are equal.
Good.
Oh, that's 1 over f equals 2 over s.
Good. And we do know what f is.
Then s is 2f, which is, we don't know what f is.
Remember, you were given the radius of
Right,
curvature.
it's 2 times 10, so it's 20. And that makes s prime also 20.
All right. So actually, the table here gave us a kind of an illegitimate shortcut. We maybe shouldn't have relied on that so much because there's a lot of work here that they'd want you to see. You can see the table is a real shortcut here, but we really shouldn't be using that as a crutch so much. This is a way to check our work or predict the answer, but we can't just say, oh, I know it's going to be 20 here. All right. So let's actually review the steps for that because that's a type of problem that's likely to come up. So what did we do here? So looking at this problem, the radius is 20. What did we figure out from that?
F is 10.
Positive 10 or negative 10?
Positive.
How do you know it's positive?
It's convergent.
Because it's concave. Good. All right. Then the next thing we used is that we have a real image that's the same size. So what did that tell us mathematically?
H prime equals h.
Actually, we don't know that. That's tricky. We don't know whether h prime is h or negative h.
Okay, yeah.
So that's probably something to stay away from. It tells us something about m.
M is 1 and negative 1?
Yeah, and which one is it, 1 or negative 1?
Negative 1, because it's a real image, so it's inverted.
Yeah, so notice we need both of these. In fact, because magnification is actually misnamed. It doesn't just reflect magnification, it also tells you indirectly whether something's real or virtual. Okay, so what we want to say here is, you might want to put this in your notes because it's a little disorganized the way we did it. First we figured out this, then we knew that because it's real, it must be inverted. Which means m is negative, and because it's same size, I guess this would be step 3, that means m is negative 1. So now, step 4, we said m is negative s prime over s. So negative 1 was equal to negative s prime over s. So that told us that s prime equaled s. Now here's where people mess up. Notice that if we were careless, we would have said m was 1, and then we would have got s prime is negative s, and the answer would come out complete gibberish. So this is the most important step to highlight here, right here. Does same size mean that m equals 1? No, it means m is 1 or negative 1. The signs here are really crucial. Also, does same size mean that h equals h prime? No, it means h equals h prime or h equals negative h prime. So that's something to really watch out for in these problems. You could solve this using h and h prime, but you have to remember that the sign is an issue. Okay, so we got this far, and then what did we do?
that into the equation.
Now we use the second equation. So then we have our fifth equation, 1 over f equals 1 over s prime plus 1 over s. But we know what f is. We already figured f is 10. So notice what we have here. We have two equations and two unknowns. You actually can't just solve this with arithmetic. You need a little algebra to solve this technically. So notice we didn't actually know until the end that s was going to come out to be 20. If you don't use the table as a crutch, it actually takes a long time to figure that out. So then we plug these into each other using the substitution method. And that's when you figured out that both s and s prime were 20?
Yeah.
Okay, so like I said, they definitely would want to see that work on the test, because that's a lot of the main part of the problem here. So the table here just is our backup to make sure we got it right, but we need to give this type of justification here. Okay. Okay, so this was a good problem to go back and try again. This is about as hard a problem as you will see, but we had some trouble with it. Okay. Get that right now. Okay, good. And we also, this was the first example that where the object started below the principal axis. So that's something to watch out for too. Suppose I tell you the image is twice as big as the object. How could you translate that into math?
M equals 2, so...
That's actually not right. The correct answer is m equals 2 or negative 2. So I just want to point out we need to know when we don't know too much. Suppose I tell you the image is 1/3 the size of the object. How would you translate that into math?
Equals plus or minus 1/3.
Yeah. Suppose I tell you the real image is 3 times bigger than the object. How would we translate this into math?
M equals -3.
How do you know it's negative?
Because it's real. Is that an enough explanation though? Just write real images are always inverted?
Yeah.
That's like an okay thing to write.
I think it's okay because, yeah, it's fair to just memorize that real images are always inverted and therefore the m is negative. But if it concerns us, we can remember this is the formula for magnification. So now remember, is this positive or negative?
Positive.
Let's say you have a real image. What does that tell us? What does that mean mathematically?
A real image.
How do we translate this into math?
Has a positive s prime.
Say it one more time.
It's positive s prime.
That's right. So what would that do to the m?
Make it negative.
And what does that mean?
That it's inverted.
So we just proved it. Okay, so I think you would probably get full credit if you just said real images are always inverted, but this is the quick way to prove it. And suppose you had a virtual image. What does that mean mathematically?
S prime is negative, so m is positive.
And what does it mean that m is positive?
That it's upright.
Yes, that m would be upright. Okay, I think you...
I don't know, I'm trying to think, because if you have like a mirror, couldn't you have a real image? Because the real image is made from like the actual light rays, right, and not the tracebacks. Like that's the
true.
definition of the real image. Couldn't you have like a real image that's in front? What am I trying to say? Oh, I guess you can, huh? Have it that's behind the mirror, or like behind the lens. Like you never have a real image that has a negative s, right? Negative s prime. It's always
Well, no, because the definition, s prime is defined to be positive for real images.
Oh.
And s prime is defined to be negative for virtual images. That's just the convention for deciding whether s prime is positive or negative. Real means a positive s prime. It's just an arbitrary convention.
Okay.
Okay. So I think it would be fair just to say we know real images are always inverted, but this is the way you would prove it. So how would we translate this into math?
M equals 1/2, positive 1/2.
How do you know it's positive?
Because it's virtual, so it's upright.
So you would want to include that in your explanation. Virtual images are always upright, so the magnification is positive. Good. How do we translate this into math?
N equals -1.
Why negative?
Because real images are inverted.
Good. This is the one that people would be very likely to get wrong. When people see that the real image is the same size as the object, they're inclined to think, oh, magnification of 1. They forget it could be 1 or -1. So these two ideas up here are very important. The magnification, knowing the magnification by itself doesn't tell you M, because M also depends on whether you're inverted or upright. So you got that right on that problem, but I just wanted to review those ideas. Okay. When an image is the same distance from the device as the object, what's that tell you about magnification?
It's 1.
Yeah, 1 or -1, same size. How about if the image is further from the device than the object?
It's shrunk.
Careful.
Right? Wait,
Here's the
if
equation.
the object is further?
If, let's say, the image is further from the device than the object,
If the image is further.
would it be magnified or shrunk? You can tell from this equation.
Magnified.
Because notice there's S prime on the top and S on the bottom. How about if the image is closer to the device than the object?
Shrunk.
Alright, so we've been using this equation, but you might not have realized what the simple intuition of this is.
Mm-hmm.
The intuition is just whoever is further is bigger.
Mm-hmm.
Right, whoever is further is bigger. You can see why that is just with simple geometry, because we're using rays like this. The shorter the distance, the smaller you are. The greater the distance, the bigger you are. So all these equations can be proven from geometry using similar triangles. So this is just saying that if you're further from the device than the object, you'll be magnified. And if the image is closer to the device than the object, you'll be shrunk. So suppose that the image is magnified. That tells you that the image must be further from the device than the object. So it helps to have that basic intuition. So when you saw that this was going to be the same size as the object, we should know from the start that it has to be the same distance from the device as the object. You can also see it from this version of the magnification equation. Whoever is at the greater distance has the greater size. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.